Hi everyone, so we're back for the second part of the morning. As we are going from this second part, I want to remind everyone that at the end of this morning, there is an EIC workshop, and so I will ask all the presenters to really stick to their time, if at all possible. And we're going to start with the first presentation post-break with William Phelps, who's going to talk to us about artificial intelligence, robotics, and quantum computing. Please take it away.
All right. Can everybody hear me? Yes? Okay. Okay, so first, CNU does not really need any kind of introduction. And yes, I did change the title of the talk. However, it's still machine learning and deep learning based. I believe this talk title is a little bit more descriptive. Just so you guys know, CNU does not really need an introduction. They've been involved in JLab since the early days. However, I am a new assistant professor at CNU in the Department of Physics, Computer Science, and Engineering. And I predominantly teach computer science, the second semester programming course. And I would like to also mention my student, Andrew Quiroga. He's an undergraduate research assistant. And we'll be going over a lot of our work today. We've got about 4 different projects we'll go over. First, I wanted to point out my research interests are quite broad: artificial intelligence, quantum information science, hadron spectroscopy, and novel detector R&D. But I just wanted to get that out there. Okay, next slide. And a little bit of background information. So basically, all of this work started, around October, November 2019. And I really wanted to highlight this artificial intelligence lunch group that we have at JLab. Okay, it hosts quarterly challenges, and the quarterly challenge that really got us involved was predicting the state vector, essentially the position and momentum of a particle in a tracking system, such as the central drift chamber in GLUOx. And that basically meant mapping the magnetic field and the energy loss of the particles within that central drift chamber into a neural network. So it seemed like a fitting place to start for us, and I'll go into our project in just a moment. As you can see, Andrew is getting his first place award, which was not the CDC. What I wanted to point out is that the AI Lunch Group is really inspiring AI research and is helping to educate our future and current scientists. So if you are interested in getting involved, I will have some slides at the end and a link to the Slack channel. So with that said, I would like to talk about the roadmap for this talk with the introduction being complete. So we're first going to start with artificial intelligence, right? So we're going to talk about 2 projects that have spawned from the work that we previously did. So first, to be the magnetic field map, we're going to talk about mapping the magnetic field into a neural network and the potential advantages there, and partial wave analysis, and a semi-autonomous robotic platform for accelerator diagnostics. That's really exciting. We just put in a proposal for that. And then we'll talk about quantum computing for reconstruction algorithms. And I just wanted to show this for those that are not familiar. It's really quite beautiful, a class 12 detector inside of Hall B. Hopefully you can see my cursor a little bit there. What I wanted to point out before we go to the next slide is the basically the 6-sector design of class 12. So in the forward detector, so the beam comes in from the right here. In this forward detector, this region on the left, you have 6 regions in which you've got torus coils separating that region. And I'll show you the magnetic field in just a moment. It's not necessary to really understand all of the hardware before going on to this. So with the background of these AI lunch quarterly problems, I thought it would be great to tackle a real world problem, right? How can we use artificial intelligence and plug into the existing framework rather than designing the framework revolving around artificial intelligence from the ground up? On the right, you can see our production magnetic field. You can see the solenoid magnetic field, and you can see the torus magnetic field. And this is a non-negligible component. I don't have the benchmarks for you right here, but of swimming and tracking, and it also had a sizable memory footprint before it was optimized of approximately a gigabyte. And basically, the question was, could we have a neural network that maps this magnetic field and have it be faster than the conventional model, or provide some sort of benefits where maybe the trade-off could be worth it? Okay, and we've got one problem with this whole project is that the current implementation is very, very fast. That's from our own David Heddle at Christopher Newport University. So let's move on. Approximating a function with a neural network. I won't go into the details about the activation functions and how neural networks work on a basic level, but here I'll show you our network architecture consisting of 3 inputs. This is one of this is a great example of a simple project here. You have inputs, which are the positions. This could be Cartesian, whatever coordinate system you want. So here we have x, y, z, and the output is the magnetic field components at that particular position. So in this case, bx, by, bz. And that is not necessarily the case for what we have implemented. One is actually you've got a different coordinate system on the input versus the output. Also, the number of layers in neurons differ from this. This is a simplified dense layer model here. And we tried everything, different models, I won't go through all of those. We also tried many different activation functions, sigmoid, PAN-H, and ReLU, and we eventually settled on using ReLU because of the performance. So let's talk about the tools of the trade here for a moment. So first of all, we really use Python, and we use the libraries that make it super powerful. So we use Keras, TensorFlow for the neural networks. We use Pandas and NumPy for data handling. And for the visualization, we use Matplotlib. We also use Pygame for a short while for interactive visualization. And one thing that I would like to mention is just how simple Python can be with these libraries. This is a sample training script that really was from the Artificial Intelligence Workshop Hackathon, but you can see in about 15 lines you can really begin training. So another thing I would like to really point out to our user group is that we have excellent machines that Scientific Computing has provided. There's 3 excellent machines that have 4 Titan RTX cards per node, and those are fantastic for training, and we use those all the time. You can have multi-GPU training there. So let's talk about the results, or preliminary results. And by the way, disclaimer, everything in this talk is preliminary since it started in the fall. So the 2 different rows that we're looking at here, maybe I can switch to a laser pointer. So the 2 different rows here, the top row and the bottom row, these are basically different slices in the azimuthal angle phi. Okay, so we've got the center in between the 2 coils, okay, and then we've got the coil center, which is actually just a slice through the actual torus coil. Okay, on the first column is the production field map, and the second column is the model prediction. Okay, and you can see it doesn't quite match up, but it's pretty close, right? This is not, we're having to trade off performance versus accuracy, and we're trying to find a nice sweet spot for that. And you can see a difference over on the right in percentage. Of course, these are for values where the production magnetic field map is greater than 1 kilogauss. And you can, okay, so it seems like we have some promising results here, and you could potentially map both the torus and the solenoid at the same time. So let's talk about the performance. So now that we have a model, we need to talk about the performance to see if we can plug it in directly or if there's going to be an issue with performance. And there's a lot of information on this page, but as far as benchmarks are concerned, but the production magnetic field is very fast, like I said. So 0.226 microseconds per sample to the magnetic field, and what we're getting is 126 and 300 microseconds for our single points that we're requesting. If we batch them and we say we want 1 million magnetic field points at a time, and we send it to the GPU or the CPU, it gets significant speed up due to the vectorization that those offer. However, that is not, this is not conducive to swimming a particle where you're not quite sure the next points that you need are going to be. Okay, so we needed to improve this. We needed to speed this up. Okay, so we looked at several libraries, deep learning for Java. All of this ultimately has to be implemented into the Java framework that the Class 12 collaboration uses, or that we use. And these are actually very, very fast inference times by industry standards. They're not doing, real-time, high performance sorts of things for the most part. And we need to improve this. We need to speed this up. And we thought that there were libraries being loaded every time you wanted to predict a single model point. So to improve that time, we actually explored multiple options. And one solution was to propagate these values ourselves using an efficient matrix library. And you can see how simple that is in the bottom. You've got your input and you've got your output. There could be performance improvements here. And actually, I see where we're missing the activation function here. It would be more difficult for, say, if you wanted to use convolutional neural networks or the like, because you'd have to add the convolution step prior to that. So our final performance benchmarks for our MagField project, before we transition to the next project, is that with a simplified model using the efficient matrix library, we're about 3 times slower than the conventional production magnetic field that we have. Okay, so we're getting in the ballpark, in the same order of magnitude, but it's still not great. So we're going to continue testing to see if this is useful and could be put into production. But let me tout some of the benefits that we could see. It could be useful for, say, open science grid, computing, where you're submitting jobs to remote clusters, and you don't want to transfer a couple hundred megabytes every time. And if you have the memory and the conventional magnetic field is actually quite fast, you could use the neural network, which is 1 megabyte, right? This particular model, which is a deep neural network, it's 10 layers of 100 nodes per layer, 100 neurons per layer. You could use that model to initialize the memory rather than reading in a couple hundred megabyte file. So there are multiple options here. It's very promising. In the future, when you write the software from the ground up, you can incorporate AI, maybe to do the entirety of swimming. But in this case, this is a great way to plug in AI where we have existing frameworks. Let's talk a little bit about partial wave analysis. I've been involved in the PyPWA project at Jefferson Labs since 2014. It is a Python-based software framework that is designed to extract resonance information from multi-particle final states, and the library was designed to be very, very flexible, but also to keep in mind that it needs to be used with polarized photon beams, such as we have in GlueX and Class 12 with the forward tagger. So Meson-X and GlueX are going to be potential users of this software, and it is very efficient. As far as this framework is concerned, it includes multi-threading and CUDA support and Bayesian optimizers. I could go on about all of the improvements. And the group members, it's led by Dr. Carlos Salgado from Norfolk State, and we've got actually predominantly computer science students working on this project. And it's been really quite successful. So take a look at the website we have, pypwa.jlab.org, and the GitHub page, and you can see that it's a very active GitHub page. One thing I should have mentioned here, if you want to install it, is a single line, conda install, I believe, pypwa. There might be one more argument. So if you're using Anaconda as your Python distribution, it's quite easy. So let's talk about the preliminary studies that will be potentially incorporated into PyPWA in the future. So our preliminary studies involved generating data sets using linear combinations of spherical harmonics, so these decay amplitudes, and we used the following quantum numbers. So angular momentum from 1 to 3, m01, and positive and negative reflectivities. You can see in the bottom right, our sample generated data. What we did is we have a histogram, a 2-dimensional histogram showing, the amplitude here. The z-axis is really just arbitrary units, and is the intensity of the wave function at that angular distribution. And here you can see our intensity function with our production amplitudes, which we're fitting for, okay, and our decay amplitudes. So we actually had quite a bit of success early on. We were able to, here we're comparing the intensity that we generated to, the generated data to the model prediction. So you can see the first column are 3 different combinations of these waves. Okay, and then the second column is the model prediction. So we give it this 128 by 128 two-dimensional histogram as an input, and then we have 9 layers of 128 neurons each using a ReLU activation, and we have 9 outputs, right, that give us the weights or production amplitude at the end. In order to deal with it, so you want to have every possible combination of waves for your training data, okay? And in order to do that, you can't possibly generate every possible combination and store that somewhere. You could end up with terabytes, petabytes of data, right, if you wanted to store all of these values. Actually, one model we had was quite ridiculous, and it was exabytes of data. So in order to deal with that, it's very much like streaming readout, right? You have a generator, and you generate that data on the fly. The generation is quite straightforward. So we generated the data on the fly, and you can see that the models match up quite nice here. I didn't want to put the fit parameters up there, but this is preliminary work and may lead to some great results in the future. And now we will transition to the robotics portion of the talk. And here we have quite a mouthful here, but it's the Collaborative Autonomous Sensor System for Intelligent Operations of Particle Accelerators, CASIO. So in order to, I would like to call it CASI actually. So from here on out, I'll be calling it CASI so I don't mispronounce it too much more. But it's about having a collaboratively autonomous mobile platform that will contain a sensor payload and would be operated in the accelerator tunnel in order to help improve, to give another tool to our accelerator operators, and also can help reduce accelerator downtime. On the right, you can see a traditional radiation survey. So here you can see, I'm not sure which LINAC, but you can see all the points in which the radiation surveys are done. And you can see that this can be a repetitive task that could take some time. And this is just one thing that we could potentially do with an autonomous platform. And this is actually a proposal that has been submitted and is a joint proposal between Christopher Newport University, Jefferson Lab. So leading this up is our own David Connor at Christopher Newport University. He's got a PhD in robotics, and I will go into his previous projects momentarily. And we also have myself and Nathan Lau at Virginia Tech. So 3 institutions collaborating on this proposal. It is, of course, still submitted and under review, but we hope, regardless, to potentially continue this project. So more about the design here, and the robot would consist of a wheeled platform and a modular arm with a sensor package mounted on the arm. So here's our wheeled platform over here. This would be a ClearPath Husky base. These are commercially available platforms that have LiDAR sensors that you can mount to them. And you can see that there's also a modular arm assembly where we would put a sensor package, which could include, we've got so many ideas for sensors that could go on there, but at the very least, radiation probes, thermal cameras, and optical cameras. And here is kind of an assembled base. And this is what, a visualization of the command system or the operator station would look like. And with all of these commercially available components that are being combined, the real task here is the software. I mean, just it's really the software and design of this. And part of that software involves collaborative autonomy. And that is when a robot and the robot operators actually work together as a team. And that means that the operators can say stop, don't do that. They can preempt that behavior. Do not do that. You're in danger. They can also say inject information. So you might have a flow chart that would have the robot going to survey particular components of the accelerator tunnel, and you might want to change it. You want to go investigate a magnet that you think is leaking LCW. Okay. And on the right, David Connor at CNU was actually the principal investigator for a DARPA team. So this is actually the Atlas, the Boston Dynamics Atlas humanoid robot that his team used in a DARPA competition. And you can see here it's operating some sort of valve. And this particular challenge involved simulating disaster relief scenarios where wireless communication could be interrupted at any point. And this is really ideal for when, say, the RF is on in the accelerator. No matter how good your network is down there, you're going to have some disruptions. So let's talk about some of the benefits here. The proposed system would improve the efficiency, okay, and it'd get rid of some routine tasks that are being done, and it would minimize the exposure to personnel from the radiological environments. It would promote ALARA principles. It would also provide a platform for novel measurements. We would have a very rich amount of data compared to previous RADCON surveys, and potentially it could run when the RF is on, or potentially even when beam is being sent. But that's further down the line. Ultimately, the goal is to reduce unnecessary accelerator downtime, automate repetitive and time-consuming tasks, and improve the operational efficiency. Preliminary estimates of the cost savings, from our accelerator division actually total $850,000 a year. So that's something that could be really useful, as well as improve the availability to our science program. And with that, I will transition to quantum computing. So just as Marcus mentioned in the previous talk, we're just seeing leaps and bounds in both conventional and quantum computing. Okay, and quantum computing is really an emerging technology. It's growing at, if you look at Nevin's law, a doubly exponential rate. And on the right, you can see a plot here showing the number of qubits for both the D-wave system, a quantum annealer, and you can see the IBM Q and Google quantum computers as well. And you can see that this is the y-axis is logarithmic, and this is over the past 10 years. So you can see we're in an exciting time where in 2020, D-Wave has 5,000 qubits that we can run problems on. Actually, at the moment, it's currently 2,000 qubits, but this year they will release 5,000 qubits. In the bottom right, you can see the D-Wave quantum computer and the processor that they're using. And these are really fantastic. They are essentially functioning as cloud quantum processing units, where you can have a Jupyter notebook and use Python and connect directly to these processors and run directly on them. And our project is Reconstruction Algorithms with Quantum Annealers. Our group members include, of course, Cristiano Finelli, Marco Battaglieri, Evaristo Alessio, and myself and my student, Andrew. In the next few years, it may be really possible to do something very exciting in quantum computing, and we believe that it is a very bright future for quantum computing. We are currently developing quantum computing-based reconstruction algorithms, and it could have the potential to revolutionize the data acquisition systems. At the bottom, you can see figures showing kind of conventional, so here would be a conventional way to find tracks and to connect the different hits. They sweep 5, 15, 10, and 40. And you can see that quantum tunneling could allow us to solve all of these optimization problems all at one time. So here's our preliminary results for track finding. On the left is classical implementation, which takes many cycles in order to actually reconstruct a track. On the right, we have a visualization with 50 tracks being reconstructed on our quantum annealer at D-Wave, and things are looking really, really exciting for quantum computing at Jefferson Lab and in the future. So, in summary, I would like to mention that we've got 3 projects here in artificial intelligence. We're making some steps. I'm looking for practical problems to utilize artificial intelligence at the lab. We've got the torus and the solenoid magnetic field for class 12. We're going to continue that project, and we're working on partial wave analysis using artificial intelligence, but it's very, very challenging with the number of parameters increasing. We will see where we can go with that. And future projects and future interests of myself and our group would be to, say, look at practical problems that have been done at other facilities, like this calorimeter response generation. So a large portion of the of simulation of Monte Carlo using JAIONT is actually calorimeter response generation. And we could potentially map that into neural networks and save significant computational resources. And of course, robotics, we hope to bring state-of-the-art robotics and AI in order to improve accelerator reliability. As I mentioned, the collaborative autonomy is really critical to this goal. You cannot simply, with the Wi-Fi connection and the wireless connection, you cannot simply strap a camera and a Geiger counter to an RC car and expect it to really succeed. And you really want to store reliable databases of the information and have it automatically logged. So it does take a bit more, and hopefully I've given you just enough information to be interested and maybe ask some questions. And of course, quantum computing is here. You can, on your computer, run on a quantum computer through a Jupyter notebook, and our preliminary reconstruction algorithms are showing some promise. So with that ends my summary, but I would like to give a brief advertisement to the AI Lunch Series, which really has inspired my work and has inspired others' work. These are weekly informal meetings. They have quarterly physics machine learning problems, kind of like a mini Kaggle sort of problems, and we've got quite a few external speakers. I highly recommend, and the only way to get information about this, or the main way to get information about this, is to join this #ML channel on Slack. So everyone that is a part of the users group meeting has most likely joined the JLab 12 GEV Slack. And I would highly recommend, if you are interested and you would like to get involved in AI, or you're currently working on artificial intelligence or machine learning, then I would recommend going here. And I have to say that the group that organizes the problems and that runs it, so Chris Tennant usually runs the AI Lunch Series, and I know Thomas Britton and David Lawrence are doing a fantastic job with the problems. I think it's a wonderful group to be a part of, and I highly recommend joining them there. So with that, I will leave this up and see if there are any questions. Hopefully I am on time.
You're on time. We have 2 minutes per question. Thanks for the nice talk.
Oh, thank you.
Forward to work with autonomous robots down in the channel. So there's a question from Bob Michael. Maybe I'll let you read it on the side. Do you see it?
Okay. Yes. Okay. So I can see it. For a given AI project, is there a good set of heuristics for picking a good network topology, like how many layers, et cetera, and as well as a good activation function, good optimizer, and a good loss function? Or is it largely a matter of trial and error? Okay, so there is somewhat of a good method. You can kind of decide if, say, a convolutional neural network would be a good choice for your particular task. So if you had an image and you wanted to solve some sort of problem, and you thought that the input being the edges of the image might be a good input to your neural network, then I would recommend using, say, convolutional neural networks. As far as after you've selected which particular type of neural network, it largely comes down to trial and error, at least in my experience. And there are some tools that you can use for that. So once you've chosen a network, you can have, say, so Keras has a tuner built in, so you can change the number of layers, the number of neurons per layer, and you can just let that train and figure out what works best for your project. But yes, I'm kind of in the same boat. It's trial and error after you've figured out the general case that you'd like to look at. And Simonetta has a question here. D-waves are not quite quantum computers. Can you comment on that? Yes. So traditional gated quantum computers are actually quite good at many tasks, and D-wave is really a quantum annealer, so very good at optimization problems. As you saw in the slide where I showed the number of qubits, we are currently not able to run on true quantum computers at the moment. So we are running on quantum annealers, though. Hopefully that answers your question. What is the radiation level you envision your robotic platform will be able to withstand? That is a good question. We were not planning to run with the beam on, but we were hoping to be able to run with a decent amount of radiation. We have not done thorough studies on that. Mainly, the initial prospect was to run with the beam off, do the survey very quickly, or go and put eyes on something like an arc magnet, a bending arc magnet, to say check the temperature, see if there's leaking coolant. But seeing as consumer hardware such as the access points down there survive, it could be possible to keep the robot at a distance and do some surveys. So that's in the future. That's beyond the first step. The main goal is to really get the software developed and to have the storage for that data. So that's a great question, though, Gabriel.
Yeah. So we're looking forward to see some of the results. Thank you very much, Will. We are going to go to the next part of the program. So can you stop sharing your screen, and Elizabeth will come in? The next part of the program is the JSA Award ceremony. Elizabeth, please go ahead.
Can you hear me, Julie?
I can hear you, and we can see your slides, so you're good to go.
Okay, very good.
Hi, Elizabeth.
Yes. Oh, okay. Hi. Yes, I got it, Lorelei. All right. Is that better? Okay. Good morning, or maybe good afternoon to some of you. I'm Elizabeth Lawson, and I manage the JSA Initiatives Fund program. I'm very pleased to join you to present several JSA awards to some of our promising and deserving young researchers and students. Let's see, Julie, I'm trying to advance, or Lorelei, I'm trying to advance.
I don't think you're in presenter mode. Did you click full screen?
Thought I did.
Do the arrow keys do anything?
Did you see it advance?
No. Yes.
Yeah. Yes.
Perfect.
Is it advancing?
Yes.
Okay, thank you. All right. The JSA Initiatives Fund program is a community building initiative. 2/3 of this year's $450,000 program, or about $300,000, support activities of the scientific user community. This is through honoraria, stipends, awards, and prizes to young researchers, support to the to the JLab Users Organization board and members, and for attendance at meetings, conferences, and workshops by young researchers and students. The JLab Users Organization Board annually evaluates applications, proposals, and posters for the JSA Thesis Prize, $2,500, the JSA Postdoctoral Research Prize of $10,000, and the JSA poster prizes of $500, $250, and $100. To start this off, the JSA Thesis Prize was established by Sura in 1999 and continued through the JSA Initiatives Fund program. Over the years, we've awarded 20 thesis prizes to recognize the contributions of graduate students. This year's prize is awarded to Anthony James Ross for his thesis, The Scattering of Spinning Hadrons from Lattice QCD. Anthony got his PhD from the University of Cambridge in 2019. His advisor was Christopher Thomas. He is currently a postdoc research associate at the University of Cambridge. So congratulations, Anthony.
Elizabeth, I just have I'm sure everyone would like to be able to upload right now. I'm sure everyone would like to be able to upload right now, but
Okay.
A little song.
Thank you, Julie. The next prize is the JSA Postdoctoral Research Prize. This award was established by JSA in 2018 as part of the Initiatives Fund program. It was one of our founding projects in the program. Over a dozen awards have been made to recognize postdocs who support the lab's scientific mission. The 2020 prize is awarded to Wenlang Li. Bill's proposal is to collaboratively develop a 12 GeV backward angle research program. Bill graduated from the University of Regina in 2017, where his advisor was Garth Huber. He's currently a postdoc researcher at the College of William and Mary, where he's been since he graduated. Congratulations to Bill. Julie, do we want to applaud? Thank you. And you'll be hearing from both Anthony and Bill after, who will be giving talks after this presentation. So now for the JSA poster prizes. There were 24 submissions in a virtual competition that took place over Slack yesterday afternoon.
I'm terribly sorry. Elizabeth, I hate to interrupt, but
yes,
could you take one moment to smile at the camera while we grab a screenshot, because this is all we can do for our group photograph.
Okay, very good. Thank you, Kent. Let me know when you're able to go.
All right. I snapped a couple there. Hopefully we've got something we will keep. All right. Thank you very much. Appreciate that.
Okay.
Thanks, Anthony.
The JSA poster prizes, as I mentioned, there were 24 submissions that we were very happy to see in a virtual competition via Slack yesterday afternoon. There was a panel of over a dozen individuals who judged these posters based on the scientific context and merit, the scientific accomplishment, contributions, and innovation, the accessibility to the broader physics community, the poster design, clarity, and visual impact, and the video presentations. So I'd now like to announce that third prize goes to ODU's Harshani Sivaratna for her poster, Measurements of the Magnetic Field Penetration into Superconducting Thin Films. Congratulations, Harshani. Second prize goes to University of Kentucky's Murchana Roy for her poster, Precision Magnetic Field Direction Measurements for Neutron Spin Structure Studies. Congratulations, Murchana. And this year's first prize poster winner is Saclais Pierre Chartagnan for his poster, Time-like Compton Scattering with Class 12. Congratulations, Pierre. And congratulations to all the poster presenters. They did a very nice job. And all the award winners that I mentioned today should coordinate with Lorelei Carlson to receive their awards. Thank you, Julie, Kent.
Thank you, Elizabeth. As we said at the beginning of the session this morning, the posters are still available for your watching on YouTube and commenting and all of that. And we encourage you to go and see them. So we should go to the next part of the program. So let me get back to the program. So our next talk is by Anthony, who's going to talk about his thesis work. So Anthony, why don't you share your slides? I see you.
Can you hear me okay?
We can hear you, but
Perfect.
not your slide, yes.
Here we go. And can you see the slides okay?
Yes, we can.
Fantastic. Thank you. So first of all, I really want to say what an honor it is to have been awarded this prestigious prize, and want to thank the organizers again for the opportunity to present my work. So what I hope to achieve in the next 20 minutes is just to give you a flavor of what I've been working on over the course of my PhD, which has been focused on computing hadronic resonances that decay into hadrons that carry non-zero intrinsic spin from first principles QCD. So what I'll do is I'll begin by giving an account, a brief account really of why we should be interested in these resonances, and present the challenges associated with performing these calculations. So I'll give a very brief overview then of Lattice QCD, and just spend the remainder of the talk then taking you through some of the details of one particular calculation that I did. Okay, very good. So as I'm sure many of you know, the vast majority of hadrons are resonances, and these strongly decay into a multitude of other hadrons in various angular distributions. Now, these typically feature in experiments as bump-like enhancements in scattering cross-sections. For example, in pi-pi scattering, we see a bump associated with the rho, and in pi-k scattering, we see a bump associated with the k star. But this is certainly not always the case, and in particular, the low-lying light scalar resonances, for example, the F0, the kappa, and the A0, remain somewhat a mystery, and they don't seem to have this canonical bump-like enhancement. Now, furthermore, they also appear to have this sort of unnatural inverted mass hierarchy, which has led to speculation over their composition. Are they tetraquark? Are they molecular-like? Or even do they exist? So certainly QCD does birth a very rich spectrum of hadronic resonances, and we really want to understand this. Now, all of these resonances that you can see have one property in common, and that is that they can and do decay into two pseudoscalar mesons in some partial waves. So, for example, S wave for the scalars, P wave for the vectors, and D wave for these tensors. There are many resonances seen experimentally that belong to what we call an unnatural spin parities. So, for example, the eta primed and the radial excited pion, the axial vectors, isoscalar and isovector axial vectors, and also the eta 2 and the pi 2. So what's different about these is they cannot decay in pseudoscalar pseudoscattering, so it necessitates something else. So, for example, vector pseudoscalar decays, vector-vector decays, or perhaps even multibody decays. But typically these multibody decays are normally mediated by an intermediate two-body decay through a vector. For example, the A1 resonance decays to rho pi, which then can decay to 3 pi. So what I'm going to talk about is really what happens when we think about vector pseudoscalar scattering. So before that, what I want to do is see what Lattice QCD has done to date. So Lattice QCD has proved very successful, especially over the last decade, in determining the properties of a number of these natural spin parity resonances. So for example, the rho resonance, which has been studied by many groups, and this is just a snippet from one of the hadspec calculations. This appears in elastic pi-pi scattering, and we see this very canonically recognized bump-like enhancement in the scattering amplitude. Now, if we take that scattering amplitude and we analytically continue this scattering amplitude to complex energies, and we search for pole singularities in the complex plane, we do find a single resonance pole that we identify as being the rho resonance. And this has a small imaginary component, and again agrees with our understanding that the rho is a narrow resonance. Now, the Hadron Spectrum collaboration that I've been working as part of has pioneered coupled channel scattering calculations from Lattice QCD over the last 5 to 10 years. And one example that really demonstrates the complications that can arise in coupled channel scattering is the pi e to kk bar S-wave scattering. So here it's apparent from looking at these scattering amplitudes that the canonical resonant-like enhancements just don't seem to appear here. I've sort of put a marker as to where the A0 mass is found in this lattice calculation, and there's nothing spectacular or remarkable about these scattering amplitudes there. And there's also many more examples of coupled channel scattering in the charm sector. But what this work has really done is given us a fantastic understanding of how to do pseudoscalar scattering from first principles lattice QCD, and to calculate the resonances. However, there's a lot more challenges that we want to understand if we're to attempt to understand particles in this unnatural parity sequence, and that's resonances that can decay via non-zero intrinsic spin mesons. So here's the challenge. One unique feature of scattering mesons where at least one meson has a non-zero intrinsic spin is that the spin and orbital angular momentums can combine in multiple ways. And this can lead, and does lead, to a multitude of partial waves that can contribute. So for example, if we just look at vector pseudoscalar scattering, for orbital angular momentum of p wave and above, coupling with the total intrinsic spin 1, we start to get triplets of partial waves. And in principle, if we had vector-vector, we would also get more and more multiplicities, because the intrinsic spin can then take total intrinsic spin 0, 1, or 2. Now, one feature of vector pseudoscalar scattering and non-zero intrinsic spin scattering in general is that we can have partial waves of differing L and in principle differing intrinsic spins that have the same JP quantum numbers, and we're going to refer to these as being dynamically coupled partial waves. So we see this in deuteron, for instance, where there's a small admixture of the D wave to an otherwise S wave nucleon-nucleon bound state. So this is one challenge. Another challenge that arises is that for these unnatural spin parity resonances, they typically appear at much higher energies relative to these lower pseudoscalar scattering resonances that I previously discussed. And a consequence of this is that there's typically far more coupled hadron channels that become viable decay modes. So in addition then to all these dynamically coupled partial waves, we can also have many coupled hadron channels, and the system becomes quite complex. So these are some of the issues that I faced when doing my PhD. An initial calculation that I carried out that I'm not going to talk about today was rho pi scattering in ISO spin 2, where we expect non-resonant weak interactions. And this helped lay down the foundations and help develop the tools and techniques needed to calculate more interacting system. And one such calculation that highlights all of these features I've just discussed is that of the B1 axial vector resonance, and that's what I want to talk about now. Okay, so this is a snippet from the PDG of what the B1 currently looks like. So from the quark model picture, for example, it looks like a UD bar 1p1 quark-antiquark pair. The B1 resonance features decays dominantly into the pi omega channel in S wave, but it also has some fraction into pi omega D wave, and that's what I'm talking about dynamically coupled partial waves. This is an example of that. We also see that there's an upper bound on the pi phi branching fraction, another vector pseudoscalar decay mode, and this upper bound that's only 1.5% agrees phenomenologically that this is an OZI suppressed decay, the phi meson being largely SS bar. Now, in addition, there's two more vector pseudoscalar channels that appear in this table. That's the rho eta and the K star K bar, and I'm going to come back to those a little bit later. I've highlighted those for calculational details that I'll explain. And there are, of course, in this table, 3-body and 4-body decays featuring pions and kaons, and again, we'll come back to that a little later on. Now, the B1 itself is a very interesting resonance. It's rich in vector pseudoscalar decay modes, and it exhibits all of the challenges discussed previously and makes it a perfect candidate for a first principles lattice calculation. So before I dive into the calculation details, I just want to give a bit of a crash course overview in what lattice QCD actually is. Okay, so first and foremost, lattice QCD is QCD. The lattice is simply a tool that allows us to compute Euclidean path integrals with systematic control. So this is achieved by discretizing space-time onto a 4D grid, which we term the lattice, and we generate then a set of gauge field configurations according to the probability distribution given by the Euclidean action. In practice, we actually integrate out these fermionic degrees of freedom analytically, so we're really just summing over gauge fields. Now, correlation functions are computed by appropriately constructing this function f, and then we average the integrand over all these gauge field configurations that we've generated. So, for example, if we wanted to compute a 2-point pion correlation function, f would be the product of a pion creation operator at some time slice t, pion annihilation operator at some later time, t prime, for example, and then we would just average that over all the gauge fields that we've generated that have a given probability distribution, and that would give us an approximation to the 2-point pion correlation function. Now, this is only an approximation, albeit a very good one in modern lattice QCD calculations, and it can be systematically improved at the price of computational cost. For example, increasing the number of gauge fields in the ensemble average, decreasing the lattice spacing, or increasing the volume. There's also a freedom here to set the parameters in the action, and it's very computationally intensive to consider light quark masses, physical pion masses, for example, in current calculations. So typically we do calculations at a number of heavier pion masses. And it's worth making this point that if we are really interested in understanding the rich structure of QCD, then we really should be interested in its properties at a range of quark masses. Okay. And lattice really gives us a way of doing that. Okay, so now we've got our correlation functions. What do we do? Well, spectral decomposition allows us to extract the finite volume energies from our correlation functions, i.e. the discrete spectrum of states in a box. Now, in particular, to determine this excited tower of finite volume energy levels, we employ a technique called the variational method, in which what we do is we compute a large matrix of 2-point correlation functions using operators resembling, for example, single mesons, 2 mesons, 3 mesons, all the structures we expect we would need to robustly interpolate all the states in an energy region. And then we diagonalize said matrix, and the eigenvalues fall away like the energies in the spectrum. Okay. Now, in the spectral decomposition, we have these operator state overlap factors that are called that really tell us how well an operator interpolates a state in the spectrum. And so the eigenvectors of this matrix that we've diagonalized, quite useful. It gives us a bit of an idea of which operators interpolate which states in the spectrum. It's not a quantitative picture, but qualitatively it helps us understand what the finite volume energy levels are, what they correspond to, and how we can interpret those. Okay, so let's have a look at this B1 spectrum as an example. So it's quite a busy picture here, so I want to take everyone through this step by step. So first of all, this is a calculation done at a box of spatial extent about 3 Fermi. Okay. And we employ here a matrix of correlation functions that's constructed from operators resembling 1, 2, and 3 meson-like states, thinking back to what the PDG looked like for the B1, and we cut off at the 4 pi threshold. Now, the solid curves in this figure indicate the position of 2 meson energy levels in the absence of any interactions. The coloured short dashed lines here are somewhat analogous, but for the 3 meson energy levels. And finally, I'll just point out that the 2 in curly braces for the pi omega highest lying non-interacting level indicates that in the absence of interactions, we would expect 2 degenerate states there. That essentially corresponds to the 3s1 and 3d1 partial wave that pi omega can exist in. Now, examining the spectra and the histograms, which show all these operator state overlap factors for each of the operators in the basis, we can see that each level is actually closely associated with its nearest non-interacting energy, with one exception, which I'll talk about. So, for example, the lowest lying level in this spectrum has a large pi omega operator state overlap factor, and it's got some mixing with these red operators, which are just single meson QQ bar operators that have the quantum numbers of the B1. We also notice, for example, that there's a level near the pi phi threshold that has a dominant overlap onto pi phi operator, and then essentially no overlap onto any of the other operators, which corresponds and is a sign of OZI suppression again, that we phenomenologically expect. There's an additional level that appears near pi-phi threshold, and we see from the operator state overlaps that it's dominated by QQ bar-like operators, and it has some mixing onto all other operators that we've used in our basis. So it looks as though it's sort of picking out all the operators mixed with this. It's just coincidence that this appears so near the pi-phi threshold. It's just a consequence of the pion mass that we're working in. But what happens is that this additional level indicates really that there is possibly a resonance here, a narrow resonance in particular. But to really understand any resonance behavior, we need to go and compute scattering amplitudes first, and then analytically continue these amplitudes into the complex plane and analyze further there. But we can learn a lot by just analyzing the spectra in isolation and thinking about what these operator state overlap factors and the position of these levels relative to the non-interacting levels tell us about the interactions in the system. So I'll flash up as well. We use a further 2 smaller volumes here. And we also use energy levels in moving frames, i.e. we project our mesons at the source and the sink to some overall non-zero momentum. And in total, this gives us 36 lattice energy levels with which to determine the coupled channel scattering amplitudes. Okay, so how do we actually compute the scattering amplitudes? Well, I've told you how to compute the finite volume spectra. We compute the scattering amplitudes using the very well-established Lucia quantization condition. So a bit of history, this was first derived by Lucia in the mid-80s, and it's been extended by a number of people to accommodate the most general 2-to-2 scattering systems. And this quantization condition relates the finite volume spectrum to infinite volume scattering amplitudes through this determinant equation that you can see, where the determinant is taken over all open channels simultaneously. And this is why, for a coupled channel scattering system, we cannot isolate a single channel in isolation. The determinant mixes all channels. Now, the connection between the finite volume and the infinite volume is seen explicitly here. The T matrix contains the infinite volume scattering amplitudes, and this M matrix is a known matrix of kinematic functions encoding the effects of the finite volume. Now, suppose we knew the scattering amplitudes, suppose we knew this T matrix exactly, then to obtain the corresponding finite volume spectrum is quite straightforward. We simply solve this determinant equation, and the roots give us the quantized energies. Going from the lattice spectra to the scattering amplitudes, however, is the non-trivial task. And a very successful approach that the Hadron Spectrum collaboration has pioneered is to parameterize the energy dependence of the scattering amplitudes in the T matrix, subject to unitarity constraints, and vary these parameters until the solutions of this determinant equation match up best with what we've computed from the lattice spectra. So once we have this best agreement, the corresponding scattering amplitudes are found, and we test this for many parameterizations of this scattering T matrix to ensure that we are parameterization independent and testing really the robustness of this method. Okay, so with all that in mind, let's take this B1 spectrum that I've shown you. We've got this method now of going from the spectrum to the amplitudes, and let's see what the amplitudes look like. So first off, what channels are we going to consider? What channels are we going to put in to our system? Well, I want to just consider a 3 coupled channel system in this case. So at this pion mass, isovectors are stable, and so the pi omega and pi phi really are vector pseudoscalar channels. Really are vector 2-body channels, sorry. The rho in this pion mass is resonant, and the K star is only just bound, and so really to incorporate those additional vector pseudoscalar channels would require a full 3-body formalism. And so what we're going to do is just ignore those for now. They actually lie at energies that are higher than where we're considering, where we're cutting off for. So motivated by the decoupling of pi phi in the spectrum plot as well, and the centrifugal barrier suppressing the D wave relative to the S wave, we also set the pi phi 3D1 amplitude to be 0. And we relax this in this calculation when we do our systematic tests, and we find that it does correspond to 0. But this is why we're taking these 3 coupled meson channels. We can see there's dynamically coupled S and D wave, and we can see that there's coupled hadron-hadron channels. So this is, going back to what I was describing earlier, a coupled hadron-hadron channel system with dynamically coupled partial waves. And the T matrix in this case would be this 3x3 sketch that I've just given here. It's a 3x3 matrix, and the determinant is over these 3 channels. So we do our parameterizations. We parameterize this 3x3 T matrix in many ways, and this is the resulting amplitude plot, scattering amplitude plot. So let's have a look. What do we find? Well, there's a large canonical bump-like enhancement in pi omega S wave to pi omega S wave, and this is what we expect for a somewhat narrow resonance. So we're seeing this canonical signature of a narrow resonance here. In pi phi, we don't see any enhancement, significant enhancement. And quite importantly here as well, we see no evidence of a ZS-like enhancement, which is proposed as the analog of the ZC3900. So we don't see any of that in pi phi. We find in the S to D wave a small amplitude here with hints of this being non-zero. And in D wave to D wave pi omega, we see this negligibly small if you look at the scale, and we see extremely small pi omega to pi phi consistent with 0, again, agreeing phenomenologically with those at I suppression. Okay, so now we've got this picture, and it's hinting that there is resonant behavior here. We do a full pole analysis in the analytically continuing to complex energies, and we do a full pole analysis to really determine the resonance structure in this sector. Okay. So analytically continuing each component of the T matrix and calculating all the singularities or in some energy range across all the Riemann sheets, we find for each parameterization a well-determined pole nearest the physical scattering region that we identify as the B1, and we find a mass of 1382 MeV and a width of 91 MeV. And remember, this is at a pion mass of 391 MeV. The corresponding residues to this pole give us the couplings, and as we expect, we find a large S-wave coupling to pi omega. We find a somewhat smaller pi omega D-wave coupling, and we find an upper bound for the pi phi coupling, which is smaller still. I'm also just going to flash up 2 other poles that we can add to this plot. One is a lattice calculation at a much heavier pion mass of 700 MeV, and we see that the B1 is a bound state here. And then I'm just putting here the PDG values that I took that you can see with the black point here corresponding to the experiment. Now, crudely, this pole trajectory as a function of pion masses is what we expect. The lighter the quark masses, the broader and lighter the B1 resonance. And to go lower in pion mass, lower in lighter quark mass, we really will have to have a fully rigorous 3-body formalism as those 3-body and 4-body channels become more relevant and open in the energy region that we're considering. So to summarize, this work has really demonstrated the capability Lattice QCD has in determining resonances in coupled channel scattering systems that feature non-zero intrinsic spin. The tools and techniques that have been developed throughout this work and other projects that I've been involved in throughout my PhD have helped expand the array of spectroscopy calculations that we can carry out in Lattice QCD. And there are really so many more interesting places to look. So in particular, there's the exotic pion 1600 with featuring decays into pseudoscalar, vector pseudoscalar, vector-vector, axial vector pseudoscalar. It's a large coupled channel scattering system. And in fact, we're currently finalizing a paper on this. So stay tuned. That hopefully will be out in the next few weeks or so. Also, in the charm sector, we can have a look at these potential tetraquark molecular-like resonances that feature, again, many coupled channel scatterings, many coupled channel scattering meson-mesons with non-zero spin. And for the first time here, we can really perform first principles Lattice QCD calculations. And of course, there's baryon-baryon and baryon-meson systems that all feature non-zero spin. And with the recent advancements in computation of correlation functions, we're really hoping to tackle these baryonic resonances in the near future. So thank you very much for listening. Once again, thank you to the selection committee, the Jefferson Lab Users Organization and Jefferson Science Associates for this opportunity and this award. I really want to give a special thanks to my PhD advisor, Christopher Thomas, David Wilson, Joe Dudek and Robert Edwards and everyone else from the HadSpec collaboration for a really fun and productive PhD program. Thank you very much for listening. Any questions?
Thank you, Anthony, and congratulations for your prize.
Thank you.
So, are there any questions in the audience? I did not see any. I had a question for you to get us started. I think you talked about one paper that you're about to publish.
Yes, yeah.
Can you tell us what you're doing right now that is different from your thesis work? What are you working on?
Yeah, right. So right now, working on the Pi1, as I said, the difficulty there is that in addition to these vector pseudoscalar scattering channels, there's vector and axial vector pseudoscalar, and the number of coupled channels really blows up. So in this system in the B1, I showed these 3 channels. In the Pi1, we're looking on the order of 8 channels, and this actually presents a problem with actually solving this determinant equation that I presented that relates the finite volume spectra to the infinite volume scattering amplitudes. And the big problem is when you have this many levels in your box and you have to reliably compute and calculate each one of these levels that are very near degenerate or in some cases totally degenerate, it's a very challenging numerical problem in itself. So that's one very sort of major aspect of my current work that I've taken on now that wasn't present as much in my PhD, and a paper that sort of followed in January, and I think it was published in May. We published this eigenvalue, eigenvector method for solving this quantization condition to really address this problem. So that's something new, and that's something that will hopefully make these larger coupled channel scattering systems really accessible.
Okay, thank you very much, and congratulations on your prize.
Thank you. Thanks very much.
We are going to move to the next talk. So the next speaker is Bill Lee, who's going to talk about his postdoctoral prize, I guess, or his prize. We can see you. We can see your screen. I think you're good to go.
Yeah. Okay. Thank you very much, Julie. And can you see my screen? And my slide is ready to go.
Yeah. Yes, we can.
Yeah. Thank you very much for presenting this prize to me, and it means a lot to me. And so today, I will be presenting this study that at the backward angle physics. So how we're gonna take this backward angle concept from JLab 12 GeV to the EIC. So here is the outline for this presentation. I will just briefly talk about what exactly is this backward angle physics, how do we access it in the 12 GeV kinematics, and what do we actually learn from studying it. And also I'll be presenting 2 physics theory interpretations to these backward or U-channel physics observables, list the plan that we're gonna accomplish in this postdoc award, and also the measure of success, and to present some progress we have made recently. So I would like to start with the Rutherford experiment. So the Rutherford experiment is, as we know, that we shooting alpha particles to the gold foils, and there are particles that go right through the gold atoms, and there are particles that is scattered at an angle, like these forward scattered alpha particles. And most importantly, in my picture, what I'm really interested in are these recoiled alpha particles. So here, I just want to bring out the concept that a full structure that of these gold atoms, we can only see it if we bring the forward angle and the backward angle observables together to yield a complete picture. As in these recoiled alpha particles really gives the stiffness of these point-like structure, as I put a quotation mark there, within the atom. So As for the case of proton, we do something very similar. We throw the accelerated electron at the proton, trying to resolve the parton distribution. As you can see that for the forward fragmented case, we have the meson that is produced in the forward angle, and we also have the backward angle produced peaks. So as I bring out this example that is showing underneath my main picture here, this is a picture from Michel Guidel's thesis, and as he was studying the real photon production of the pi plus meson, you can see that the forward angle peak at a very low t that is demonstrated by this t slope that is contributed by the exchange of the pion in the forward angle. And as I would go up to t, as you can see at the very kind of backward kinematics, you also have a rising in cross-section. So this demonstrates as the baryon pole exchange, where you have a point-like structure or hard structure that is in the plateau region. So this is a very good example in our field how you can bring the forward and backward angle observables together to yield a complete transition of the proton structure from soft to the wide angle hard structure, then in the end to the soft structure again in the backward angle. So in Jefferson lab, we study the evolution of proton structure using 4 different parameters. We have the parton momentum fraction x, that is normally just being dictated by the energy or the beam energy that is available. So we are in the valence quark distribution region. And also that we have the Mandelstam variable S, which is in here is the W, where that dictates if a process that is in the resonance region or not. And then we also have the Q squared that manifests itself as the wavelength of the probe. That is, we can see it as the resolving power of our probe, and also we have the Mandelstam variable T that is inversely proportional to the impact parameter B. So in Jefferson lab case, then if we want to probe harder into the nucleon distribution, then we just bring up in Q squared, and then we go higher in T, so we probe harder into the nucleon. Then that kind of bring down, let's say, the impact parameter B, so we look harder into the nucleon structure. But notice there's something missing here, is that what does the U represent? Is there any special role for the Mandelstam variable U? So I give an example of my studies in Hall C from 6GeV, trying to understand if does U actually carry any meaning. So this example was the pion form factor experiment from Hall C 6GeV. As in this example, we have the electron coming in, interact with the liquid hydrogen target. The electron recoil into the short orbit spectrometer, and a pion that is produced in the forward angle, as you can see. The pi plus travels into the high momentum spectrometer, leave the nucleon, spectating nucleon behind at the target station. And this is the primary reaction from the pion form factors experiment. In addition, we get something for free, which is we have a omega that is produced as a result of the electron proton that is going forward. So very interestingly, this reaction is not elastic. You actually have a omega that is produced. We'll see in the next page. This is my thesis topic. And the kinematics coverage of this experiment, you can see, is that we have the resonance that is above, we have the W that is above the resonance, and we have 2 independent Q squared settings, and we have 2 epsilon settings for each Q squared that is optimal to perform the LT separation. On this page, I'm showing you a log post on the left-hand side, as you can see indicated by this boundary box. This is a log post from 2003. And you can see that the forward angle pion that is registering on the SOS HMS coincidence as this very primary large peak here. And then we have also a coincident proton that is detected. And as I mentioned, these proton events are not elastic events. And if we take these events doing the missing mass reconstruction, we can see that omega that is showing very distinctively above a very broad background. If you are experts or with your expert's eyes on LT separation, some of your experts can probably immediately tell that the low epsilon and the high epsilon at this particular Q-squared is very interesting, is that the yield has almost no change, indicating that the longitudinal cross-section is almost zero. So during my analysis, I used five different simulations, trying to simulate what exactly is the background underneath the omega. As you can see, an example plot here. After I do my event selection, background reduction, and you can see that the two epsilon settings, the red being the high epsilon cross sections. This is the unseparated cross section plotted against the modulation. I can see that the high epsilon data is in red, and the black data are the low epsilon settings. And you can see there is almost separation between them, indicating that sigma L is almost zero. And this is confirmed by the L to T cross-section ratio at the lowest UBN here. You can see two different Q-squared settings, and we actually demonstrated that this transverse cross-section is dominant over the longitudinal at Q-squared as low as 2.2. And this is a very important result, as we will be coming back to it. So another very interesting result we have found with our data is that there is a very sharp rise for our omega cross-section when we plot it on the same scale as the class 6 data was published earlier. You can see a very distinctive T-channel peak and a very distinctive U-channel peak offered by our data. So here, I would like to introduce the very first exchange of approach to understand these U-channel observables. The first is the Laget study in 2018. As you can see that he updated his Jean-Marc Laget model in 2018, and he account for our data, as my cursor is pointing at the Q-squared of 1.75 and the Q-squared of 2.35. And one interesting findings from his study is that he cannot just explain the U-channel rising with just the nucleon pole contribution, which is labeled in this diagram here. As you can see that the baryon exchange pole contribution is only this black dashed curve here, where if you want to completely fit our data in the U-channel, he found that he has to include additional, as he described it, row exchange, which representing this row meson produced and is kind of being rescattered inside of the nucleon diagram. So this is in progress, and he is aiming to publish this work very, very soon. And one unfortunate thing about his study is that he did not attempt the LT separation results as we have in the data. So I'm happy to announce that there is a separate Reggie approach effort that is initiated by one of our Korean colleagues, and he will be attempting to use the Reggie-based model to predict LT separated cross-section. And the second approach that how we can look at these U-channel peaks are the GPD-like hard structure or hard exchange diagrams. So GPD, as we understand it, is it's like a hadron tomography of a proton, but it's predominantly studied based on the forward angle observable or forward angle measurements and data. In order to comprehend the U channel or T equal to T max scenario, or even the modest T, we really have to borrow a concept that was discovered by Frankfurt and Strickland in 2003, which described a scenario where a fast proton and the soft meson is produced, is known as a skewed parton distribution. And at the extreme case, at the U-channel kinematics, this framework become known as the super skewed parton distribution. And independently rediscovered by Bernard Pierre and others, so they have came up with a kind of the backward angle factorization scheme known as the meson to nucleon transition distribution amplitude, as I have shown a picture of that here. You can see that this structure here will have a proton coming in, turning this proton into a meson, and then 3 quarks of this proton will then fly forward, absorb all of the momentum by the virtual photon and hydronize in the forward angle, and leaving omega behind. So one of the is very interesting aspect of the TDA factorization scheme is that it produced 2 qualitative predictions that we can test experimentally. The first is that it predicts the transverse cross-sections have to scale as 1/8 to the power q squared to the 8th scaling. This is very classic scaling behavior. And the second prediction is very powerful. It predicts the sigma longitudinal cross-section sigma t will dominate longitudinal cross-section sigma L. As you can see from our data that I presented a little earlier, is that we do see the sigma t dominant sigma L at for the omega production case at a 2.2 q squared, where we do not have the scaling behavior. However, the scaling behavior evidence come from earlier studies from class 6 with pi plus production. As you can see, that their cross-section scales almost exactly as predicted by the TDA, which is demonstrated in this blue band and light blue band. And I think these evidence just give us the courage to develop a comprehensive validation program for the TDA. As I have listed on the right-hand side, a list of meson productions we can test the validation of TDA. And these there are 3 phases for our current plan, which the first phase or stage 0 involves looking for the U-channel peaks for all of the listed meson productions, and then to test their behavior in U-channel fulfills the predictions from the TDA. As you can see that the confirmed these predictions are confirmed by data. I have a double tick here, and some of the single tick means that we may have data that is available to perform the studies. So these will be the parasitic data from Hall C. And we also proudly announced that we are developing a very specific dedicated studies for the Pi0 testing TDA validations for the PAC48. So as a list of tasks for this award, so we are inviting Dr. Kirill Semenov-Tenshansky for a research trip to the United States as the TDA experts, so we can deepen the discussion in the U-channel physics. together, we will be developing a coherent and a comprehensive 12 GeV strategy, which is desperately needed, as we know that the 12 GeV is well on track, and it's very important for us to come up with a priority list among these a large number of observables, trying to prioritize our time and effort and also the resources. This includes a potential U-channel DVCS program. And also we would like to invite him to work on some cross-section predictions on the 12 GeV and EIC kinematics. And I personally, along with Garth Huber and Justin Stevens, will be hosting the very first U-channel physics workshop at Jefferson Lab. To measure our success, we would like to complete and publish the workshop white paper on our the results of as a discussion from our workshop. Set that as a strategy for the backward angle physics for 12 GeV Jefferson Lab. We'll be presenting and publishing the backward angle pi0 feasibility studies, which I will present a progress today to you all. And also, I would like to work with Kirill to complete the relevant sections in the yellow report on the U-channel pi0 production. And we will be presenting the PAC proposal to PAC 48. And I'm proudly happy to announce that this has already been completed. So how do we take the U-channel physics from Jefferson Lab 12 GeV to the EIC? As you can see that we selected the pi0 as an example study. As you can see that our PAC 48 proposal is in this pink dots here. And this is notice that we have selected the W of 3, which is S of 10. What's interesting about this kinematics is that we also have a Panda program that is doing exactly the same thing as they are studying the small Q-square scaling. And we will be able to, at the PAC 48 at 12 GeV, study the Q-squared at these available, which is 2 to 6. And at the EIC, we can even further to look at the Q-square scalings from 6 to 10. So I will be present an update on these two fronts here. So as for the PAC 48 proposal on the backward U-channel pi0 productions, as you can see that the measurement will be performed Hall C, and electron and proton will be in coincidence, and the pi0 will be produced in the backward angle. And we will be using missing mass reconstruction technique. As you can see, the missing mass is on the top right-hand side corner. And the only known physics background underneath the pi0 peak will be the DVCS, which is projected to be several magnitude lower. And these are the kinematics on the left-hand side and the middle left-hand side, what we're trying to perform our study on. So I'm very happy to announce that this has been submitted to PAC 48. And as for the pi0 program in U-channel at EIC, we are utilizing the 100 GeV proton collide with 5 GeV electron. Very uniquely that this pi0 will not go to the wide angle detector, but it will be travel towards a ZDC along it will be travel towards the ZDC where the proton will be emitted in the small angle forward, which is exactly the opposite of the T-channel any other T-channel process. As you can see that we are targeting at the U prime of 0 GeV. And the question is that, can these decayed 2 photons be detected considering the realistic angular acceptance of the ZDC? So based on my preliminary study is that we provided answer is that yes, we can detect it. As you can see that I call it the the two photon donuts. These are the events that with pion. These are the events with both photons that is being detected, and the edge of this rim or this donut representing the boundary of the ZDC. And yes, if we have the ideal trigger, which is which is electron, proton, then 2 gamma, and this channel should be very clean with very little background, but it will be with reduced efficiency depending on what momentum of the pion is generated. So the next step for us will be to roll this, to proceed to the full simulation to look at the realistic efficiencies and the PIDs. And I'm very happy to announce, happy to let everyone know that the ESA Fellowship Award that recently will help us completing the yellow report and the feasibility studies as well. So here is just a little bit of an advertisement for the first U-channel physics workshop. As you can see that this will on track on this workshop, despite the coronavirus situation, is still on track for September 21st and the 22nd. And the ink deco page is now available. I invite you to take a look at it. And we have the representative from all 4 halls, so you don't get confused that thinking I'm the only person that's working on the U-channel physics. No, we actually have a representatives from all 4 halls, and we have very exciting opportunities and theory perspectives. As you can see that I colored these opportunities in different color code. Yeah, please take a look at our events. And as a result of this workshop, we'll be presenting a white paper outlining what we have learned, also the discussion on what would be the U-channel physics strategy for the 12 GeV. So this is as a last slide. I would like to end on a lesson from the past. So the figure in the center here shown is from the DESI experiment, from the DESI spectrometer experiment from 1984. So in this U-channel spectra, you can see pi 0, eta, and omega and rho. And as inspiration, I'm pretty sure, as inspiration from this U-channel study, it actually inspired some very early U-channel studies at Jefferson Lab, which I'm picking a few examples. So this is really a time for us to resurrect the U-channel meson productions at the 12 GeV kinematics and the future ESC. And all of our activities here is to inspire a wave of backward angle physics measurement in the very near future. And thank you for all your attention. Yeah, so that's my end of my presentation. And thank you to all of these people who have supported me along this way. Yeah, thank you.
Thank you, Bill. Thank you for this nice presentation and also for all this work on the U-channel processes. We wish you good luck. I don't see any question in the chat, and we're kind of running out of time, so
sure.
I'm sorry. We're going to move on right away. So I think Lorelei want to say a few words.
All right.
All right. Bill, do you want to turn off your video? So Lorelei, yeah, super, thanks.
All right. Can you see it?
Yes, we can.
All right. Perfect. So I just we made some slides for the poster session that I'm just going to go over really quickly. We have so many people that we want to thank. So here are some comments that we pulled off this Slack channel yesterday. At one point, I saw over 100 people on the channel. We had some of the videos that had over 200 views. It was super exciting. I hope you all really enjoyed it. Based on the feedback, we definitely know that a lot of people really did enjoy it. Here's our special thanks page. I won't read out all the names. Our judges, obviously, we could not have done it without them. Our planning committee, we took the idea of not having a poster session at all, and we changed it into something that I think was a super success. Great job to Amy. I know the final round judges made comments about how well organized it was and how successful it was from her instructions. So great job, Amy. And also to JSA, obviously we wouldn't be able to do this without them, and to be able to award prizes. We are always super grateful to that. And I think Amy wanted to make a couple comments too.
Yeah, hi. I just want to say thank you so much, Lorelei. I could not have done this without you. Thank you to the judges, and thank you to the rest of the planning committee who helped us take the idea of a virtual poster session from its infancy into what it became. Like, of what it could be, and I could not be happier with the result. And thank you to everyone who entered. Thank you to everyone who participated, who asked a question, who hung out in the Slack channel. It was so great to see. Thank you so much.
Absolutely. Thank you.
Especially, one more thing. Of course, Lorelai's worked overtime on this, so we always have to make sure to give props to all of her extensive work on this.
Thanks, Ken.
Very good. So we almost wish we can do that again. All right. So I just want to say, I'm going to terminate the session, but Bill and Anthony, can you please stay on? So thanks for all the speakers for this morning session. Congratulations to the award winner again. The EIC workshop just started, so if you want to jump into that, go ahead. The links are on the program. And the main session this afternoon is starting again at 1:30. We are looking forward to see you all there. Thank you. So we're going to get Bill, Anthony, Jerry, and Elizabeth back on the screen. Yes, I see you coming. Elizabeth, we see your camera. Maybe you have a post-it on top of it.
Uh-oh.
Julie, do you see me?
Not yet.
Okay. I have my video on.
Do you want to try to turn it off and on again?
Turn it off and on? Okay.
Jerry, we see you.
You see me, Julie?
I see you. You look very nice.
It says that I'm on, Julie.
Right, that's a perfect picture. You're all like a black screen. Do you have something in front of your video?
Oh, you're right. You're right. Sorry about that. Yeah. Sorry. That's when I am in my pajamas.
Hey. Do you want to?
All right. Don't make it right.
Smile.
Great. So, yeah, if you guys could just give me a couple more, just look at the screen and give me a smile or your coolest expression. I really appreciate it. Thanks a lot. I've got a couple screenshots there, so hopefully that gives us what we need.
Great. Thanks a lot. Cheers.
All right.
Thank you. Thank you. Bye.
Welcome. The nice talks.
Thank you.
Bye. Bye, Jay.
Julie, I think I was not on the picture, but that's because I joined as a guest.
We see you on the picture, so I think Kent was probably able to.
Okay.
We got you.
Okay, that was a good session. Thank you.
Thank you for joining.
Yep. I'll hang up now.
Okay. Anything else?
I think we could pause the broadcast with the.
Okay, I'm going to send an announcement real quick.
So I know everyone said how well it turned out, but I think Laura, you did really great, and Kent, like you did also really great for all the support during the session. Congratulations.
I'm glad you're able to share it. I'm glad the internet held up well enough.
Yeah.
Real quick.
Yeah.
Go
Okay.
ahead.